A pleasant morning, everyone. Before we discuss our topic this morning, let me introduce myself to you first. I am Darius E. Montanio, a psychology and guidance major.
And I am Chris Peter Apumayana, a curriculum development major.
And for the outline of our presentation, we will start with what is MANOVA,
And that is to be followed by the purpose of using MANOVA.
Its assumptions and limitations.
We have the methods of testing the assumptions.
We will also be discussing the test statistics for MANOVA. We have Wilks lambda, the Pillai's trace, the Hotelix trace, and the Roy's largest root.
And that is to be followed by steps in performing analyses.
And before we end, we're going to summarize the topic by presenting once again the rules of thumb in using MANOVA. Despite the difficulty that we encountered in preparing for this presentation, we will try our very best to explain the topic about MANOVA. I am sure that Sir Dan is also with us to clarify or enlighten if there are ideas that might be unclear to you, my dear classmates. So I find this topic very challenging, but I am still very grateful for this experience because I am able to appreciate the beauty of using MANOVA in doing a research. So let us begin the discussion by defining what is MANOVA. So MANOVA stands for Multivariate Analysis of Variance. It is actually designed to test the significance of group differences, just like the ANOVA or the analysis of variance. The only difference is that MANOVA can include several dependent variables, while in ANOVA it can handle only one. MANOVA is just actually an extension of the common analysis of variance. In ANOVA, differences among various group means on a single response variable are being studied. And in MANOVA, the number of response variables is increased into two or more. And the hypothesis concerns a comparison of vectors of group means. So unlike the univariate situation in which there is only one statistical test available, which is the F ratio, the multivariate situation provides several alternative statistical tests. Also, in MANOVA, the dependent variables should have some degree of linearity and share a common conceptual meanings according to Stevens of 2001. So in MANOVA, it assumes linear relationships among the dependent variables within a particular cell. So we should also study the scatter plots of each pair of dependent variables using a different color for each level of a factor. Linearity can actually be positive or negative. So say for instance, if we are going to imagine using the Cartesian plane, the x-axis and the y-axis. So when one variable increases while the other variable decreases, we can say that there is a negative linear relationship existing, meaning there is a negative linearity. And when both variables increase or decrease concurrently at a constant rate, a positive linear relationship exists. And a linear relationship is a trend actually in the data that can be modeled by a straight line. And the clear advantage of a MANOVA over a univariate ANOVA is, of course, as what I have mentioned earlier, the inclusion of multiple dependent variables. To give a clearer illustration, here is the picture of the comparison between ANOVA and MANOVA. On the left side is the ANOVA, while on the right side is an illustration of MANOVA. As we can see, there is the presence of IV and DV, our independent variable and dependent variables. Let's just have a short review. What is an independent variable? It is the variable that we think is the cause, while a dependent variable is the effect. And the independent variable is the variable that we researchers or experimenters manipulate or change and is assumed to have a direct effect on the dependent variable. The dependent variable is the variable, on the other hand, being tested and measured in an experiment and is dependent on the independent variable. So in the picture, or in the illustration rather, in ANOVA, the independent variable is the level of education. And this is same is true as well in MANOVA. And it is grouped or classified into three. Okay, we have secondary, college, and graduate school. While the dependent variable for ANOVA is test score, and in MANOVA, there are two dependent variables, and these are test score and English proficiency. Earlier, we had the one-way ANOVA, so this time I'm going to show you an illustration of the two-way ANOVA versus two-way MANOVA. So for the independent variables of the two-way ANOVA, so we have two. Okay, so these are level of education, which are grouped into three: secondary, college, and graduate school. Okay, another independent variable is the learning style, which is actually classified into four. So we have the VARK. V stands for visual learners, A stands for auditory learners, R stands for reading and writing inclined learners, and K stands for kinesthetic learners. Okay, we only have one dependent variable, which is the test score. So that's the two-way ANOVA. On the other hand, we have on the right side an example or an illustration of the two-way MANOVA. As you can see, there are also two independent variables, same with two-way ANOVA. However, okay, there are two dependent variables. All right, so going back to the definition of ANOVA, and it examines the differences among various group means on a single response, which is the test score, while the MANOVA, it examines the differences among various group means on two or more dependent variables. So in the case of the MOVA and MANOVA in the illustration, so these are dependent variables are the test scores and the English proficiency. So what is the purpose of performing multivariate analysis of variance? So there are two reasons, or two major reasons, why a researcher should be interested in using more than one dependent variable when comparing treatments or groups based on differing characteristics. So first one, any worthwhile treatment or substantial characteristic will likely affect participants in more than one way. Hence, there is a need for additional criterion measures. Okay, another reason, number two, is the use of several criterion measures permits the researcher to obtain a more holistic picture and therefore a more detailed description of the phenomenon under investigation. So this stems from the idea that it is extremely difficult to obtain a good measure of a trait, say for example, math achievement, self-esteem, etc., from one variable. That's why multiple measures on variables representing a common characteristic are bound to be more representative of that characteristic. In MANOVA, okay, a new dependent variable is created, which is a linear combination of the original measured dependent variables combined in such a way to maximize, of course, the group differences. And by developing a linear equation where each measured dependent variable has an associated weight, and when combined and summed, it creates maximum separation of group means with respect to the new dependent variable. So MANOVA assumes that there are linear relationships among all pairs of dependent variables, all pairs of covariates, and all the dependent variable covariate pairs in each cell. Therefore, when the relationship deviates from linearity, the power of the analysis will also be compromised. So we have to take note, however, that MANOVA is extremely sensitive to outliers. Outliers may then produce either a type 1 or a type 2 error and give no indication as to which type of error is occurring in the analysis. So let's just have a short review. So what is a type 1 error? It is also known as a false positive and occurs when a researcher incorrectly rejects a true null hypothesis. Okay, this means that your report that your findings are significant when in fact they have occurred by chance. And a type 2 error, on the other hand, is also known as a false negative and occurs when a researcher fails to reject a null hypothesis which is really false. This is an illustration or an example of a linear equation. And by developing this linear equation where each measured dependent variable has an associated weight, and when combined and summed, it creates maximum separation of group means with respect to the new DV. So after that new DV is created, an ANOVA will then be conducted on this newly created variable. And a specific example will be discussed further by my partner, Sir Chris.
Let's try to consider this. Assume we wanted to investigate the differences in worker productivity as measured by income level, which is our dependent variable 1, and hours worked, that is our dependent variable 2, for individuals of different age categories, and that is our independent variable. Our analysis would involve the creation of new DV, which would be a linear combination our new DV of our subjects' income levels and number of hours worked that maximizes the separation of our age category groups. Our new DV would then be subjected to a univariate ANOVA by comparing variances on the new DV for the various groups as defined by age category. But before going further, it is very necessary to look into the different assumptions and limitations. Again, we have to remember that these assumptions should be satisfied, and any violation later on would really affect our data. First, the observations within each sample must be randomly sampled and must be independent of each other. Next, the observations on all dependent variables must follow a multivariate normal distribution in each group. Third, the population covariance matrices for the dependent variables in each group must be equal. This assumption is often referred to as the homogeneity of covariance matrices assumption or the assumption of homoscedasticity. And lastly, the relationships among all pairs of dependent variables for each cell in the data matrix must be linear. As a reminder here, the assumption of independence is primarily a design issue, not a statistical one, provided the researcher has randomly sampled and assigned subjects to treatments. It is usually safe to believe that this assumption has not been violated. In this case, we will focus our attention on the assumptions of multivariate normality, homogeneity of covariance matrices, and linearity. This time, let's discuss the methods of testing the assumptions. Multivariate normality is a difficult entity to describe and even more difficult to assess. That's why for the initial screening, it is very important to assess the univariate normality for all variables. At the same time, there should be an examination of all bivariate scatter plots to check that they are approximately elliptical. Remember, the size of about 20 in the smallest cell should be sufficient to ensure robustness to violations of univariate and multivariate normality. Assumption of equal covariance matrices is necessary condition for multivariate normality. Remember, the failure of the relationship between two variables to be homoscedastic is caused either by the non-normality of one of the variables or by the fact that one of the variables may have some sort of relationship to the transformation of the other variable. That's why checking for univariate and multivariate normality is a good starting point for assessing possible violations of homoscedasticity. Possible violation of this assumption may be assessed by interpreting the results of boxed test, and that will be given to us by the SPSS. And take note of this, that if homogeneity of covariance is violated, a more robust multivariate test statistic, which is Pillai's trace, can be selected when interpreting the multivariate results. Linearity is best assessed through inspection of bivariate scatter plots. If both the variables in the pair are normally distributed and linearly related, the shape of the scatter plot will be elliptical. So remember, assessing linearity by means of bivariate scatter plots is an extremely subjective procedure. In situations where non-linearity between variables is apparent, the data can once again be transformed in order to enhance the linear relationship.
Let us now proceed to the test statistics for MANOVA. So there are actually four test statistics for MANOVA. So these are: one, Wilks lambda, or the most commonly used criterion. We also have the Pillai's trace, the Hoteling's trace, and the Roy's largest root. So for a particular p-variable multivariate test, assume that the matrices H and E have smaller H and E degrees of freedom, respectively, and for test may be defined as follows. Okay, for the H, it is actually called the hypothesis matrix, and E is the error matrix. So these matrices may be computed using a number of methods. So if you are using the SPSS, we use the standard GLM, or the General Linear Models approach, in which a sum of square and cross products matrix is computed. So this matrix is based on the dependent variables and independent variables generated for each degree of freedom in the model. Okay, here is the formula for the Wilks lambda, and I will no longer delve on discussing the details of this formula. I will just give the background. What is Wilks lambda all about? Well, Wilks lambda assesses the differences between two or more groups on multiple variables at once. It is actually the multivariate version of the F-test statistic in one-way ANOVA, which examines the differences between multiple groups on one variable. In other words, Wilks lambda test for differences between groups on a vector or variables, vector of variables rather. So there are 6 critical assumptions. Just like earlier, we discussed the assumptions in using MANOVA. In performing the Wilks lambda alone, there are also assumptions that we have to observe. First one, the dependent variables in question are measured on an ordinal or continuous scale. And a common example of ordinal variables is the Likert scale. Like for example, a 5-point scale from strongly disagree to strongly agree. Continuous variables are quite common, such as body weight, exam scores, blood pressure, heart rate, etc. Next one, the subjects are independent of each other. So this relates to the sampling design of the data collection process and hence cannot be directly evaluated with the data. Next, relationships between the continuous variables of interest, if they exist, are linear. This can be visually inspected by plotting every pair of the variables with a scatter plot. Next one, variances and covariances of the continuous dependent variables are equal across groups. Another, there are no outliers in the sample. This can be visually inspected using box plots or identified quantitatively using Mahalanobis distance. So let me give you a background about what Mahalanobis distance is. It is just the distance between 2 points in multivariate space. It also measures distance relative to the centroid, a base or central point, which can be thought of as an overall mean for multivariate data. Right? The last assumption is that the dependent variables are normally distributed within groups. In practice, it is common that this condition is not met, but Wilks lambda is fairly robust to moderate violations of the normality assumption. Okay, let's proceed. The second one is the Lawley-Hoteling's trace. Okay, so this is the formula. So Lawley-Hoteling trace is the sum of the eigenvalues of the test matrix. So it is actually a positive valued statistic for which increasing values indicate effects that contribute more to the model. And Hoteling's trace is always larger than the Pillai's trace, but when the eigenvalues of the test matrix are small, so these two statistics will be nearly equal. This indicates that the effect probably does not contribute to the model. Okay, we can actually calculate the Lolly-Hodgling trace by summing the characteristic roots. Okay, I have here an example. Okay, so we have the eigenvalues and canonical correlation. Okay, root 1 is 0.892 and root number 2 is 0.005. So we just have to add those two values, and if we're going to find here the Hodgling is equal to 0.89723. Okay, by the way, let me give you a definition of what is this eigenvalue, all right, or eigenvalues and canonical correlations. So this section of output provides the eigenvalues from the product of the sum of squares matrix of the model and the sum of squares matrix of the errors. So there is one eigenvalue for each of the three eigenvectors of the product of the model sum of squares matrix and the error sum of squares matrix. So let's now proceed to the Pillai's trace. Okay, so what is this Pillai's trace? Pillai's trace is used as a test statistic in both MANOVA and MANCOVA. So this is actually a positive valued statistic ranging from 0 to 1. Okay, increasing values means that the effects are contributing more to the model. And with that, you should reject the null hypothesis for large values. And Pillai's is one of the several test statistics used in MANOVA. So when are we going to use this test? This test is considered to be the most powerful and robust statistics for general use, especially for departure from assumptions. So what we mean by that is that if there are deviations from assumptions. Okay, for example, if the MANOVA assumption of homogeneity of covariance is violated, then this is the best option that we can use. It is also a good choice when you have uneven cell sizes or smaller sample sizes, okay, most especially when the n is small. However, when the hypothesis degrees of freedom is greater than 1, Pillai's tends to be less powerful than the other three test statistics. If you have a large deviation from the null hypothesis or the eigenvalues have large differences, Roy's maximum root is a far better option. So we will also discuss the Roy's largest root. So this is the formula of the Roy's largest root. So Roy's largest root is the largest eigenvalue of the test matrix. Thus, it is a positive valid statistic for which increasing values indicate effects that contribute more to the model. So Roy's largest root is always less than or equal to Hodgling's trace. So when these two statistics are equal, the effect is predominantly associated with just one of the dependent variables. Therefore, there is a strong correlation between the dependent variables, or the effect does not contribute much to the model. And by the way, Roy's largest root goes by many other names, including Roy's largest characteristic root, Roy's greatest root, Roy's maximum root, or Roy's criterion. And we also have to be reminded about these ideas that Roy's largest root is always smaller or equal to Hodgling's trace. If they are equal, it may mean one of the following. The effect is mostly associated with one dependent variable. 2, there is a strong correlation between dependent variables. 3, the effect has a negligible contribution to the model. Alright, so which test, among those 4 test statistic to use? Okay, when the hypothesis degrees of freedom H is 1, all 4 test statistics will eventually lead to identical results. However, when H is greater than 1, the 4 statistics will usually lead to the same result. When they do not, the following guidelines, okay, from Tabachnik of 1989 will be of help. All right. So what are these guidelines of Tabachnik that we have to follow? Tabachnik actually had the following assumptions when we are using a MANOVA. So these are the following. One, the response variables are continuous. Two, the residuals follow the multivariate normal probability distribution with means equal to 0. Three, the variance-covariance matrices of each group of residuals are equal. Number four, the individuals are independent. So MANOVA is robust to modest amount of skewness in the data. A sample size that produces 20 degrees of freedom in the univariate F-test is adequate to ensure robustness. Non-normality caused by the presence of outliers can cause severe problems that even robustness of the test will not overcome. So, Wilks lambda, Lolly's trace, and Roy's largest root are often more powerful than Pillai's trace if h is greater than 1, and one dimension accounts for most of the separation among groups. Pillai's trace is more robust to departures from assumptions than the other three.
So moving forward, let's do the steps in performing analysis. Number 1, test for homogeneity of variance, covariance, that is our box test. If homogeneity of variance covariance is assumed, utilize the Wilks-Lambda statistic when interpreting the multivariate test. If the assumption of equal variances is violated, use Pillai's trace. So typically, if box test is significant at p-value 0.001 and group sample sizes are extremely unequal, then robustness cannot be assumed. So our SPSS will give us this box test data. Second, examine the significance, the F ratios and p-values of factor interaction. And lastly, evaluate the F ratios and p-values for each factor's main effect. Remember this, if multivariate significance is found, interpret the univariate ANOVA results to determine significant group differences for each DV. If univariate significance is revealed, examine the post hoc results to identify which groups are significantly different for each DV. So this time, let's take a look at the sample problem and its result. For our question number 1, are there significant mean differences in worker productivity as measured by the combination of income and hours worked for individuals of different ages? Number 2, are there significant mean differences in income levels for individuals of different ages? If so, which age categories differ? And lastly, are there significant mean differences in hours worked for individuals of different ages? If so, which age categories differ? Okay, let's try to look back again our independent variables and our dependent variables as shown in the picture. For step 1, the box test for homogeneity of variance covariance, as you can see in the illustration, box test is not significant. So we're going to use Wilks-Lambda criteria. Our p-value here is 0.648. For our second step, we're going to look the F ratios and p-values of factor interaction. So here we're going to look specifically the Wilks-Lambda data, and it shows there that the p-value is 0.00. So it indicates that age category significantly differs from the combined DV. So it indicates group differences in age category with respect to income and hours worked per week. So in our previous slide, it was mentioned that age category significantly differs from the combined DV. So in this case, for the F ratios and p-values for each factor's main effect, or the univariate ANOVA summary table, we're going to look which among these two dependent variables is greatly affected by age category. So as we can see here, the p-value of income is 0.00, and the p-value for hours worked is 0.919. So it indicates that age category significantly affects income but not hours worked. So to recap for the result, again, the univariate ANOVA results were interpreted using a more conservative alpha level 0.025. So results reveal that age category significantly differs only for income and not for hours worked per week. As what was mentioned just a while ago, since age category significantly affects income but not hours worked, so we're going to have our post hoc test. But if age category does not significantly affect both income and hours worked, we don't need to go further and have our post hoc test. So in this case, because as I mentioned just a while ago, that age category significantly affects income but not hours worked, we're going to consider this data for the post hoc result. So the post hoc results reveals that income of those 18 to 29 years of age significantly differs from all other age categories. In addition, income for individuals 30 to 39 years differs from those of 40 to 49 years.
So before we end our presentation, let us have some rules of thumb in using MANOVA. Okay, first one, it's about the decision processes for MANOVA. Well, we have learned earlier that MANOVA is just an extension of ANOVA that examines the effect of one or more non-metric independent variables on two or more metric dependent variables. So MANOVA has the advantages of controlling the experiment-wide error rate when some degree of intercorrelation among dependent variables is present, and providing more statistical power than ANOVA when the number of dependent variables is 5 or fewer. Okay, we should also bear in mind that the researchers should include only dependent variables that have strong theoretical support. Research designs for MANOVA. So cell groups are formed with a combination of independent variables. So we have, for example, a 3-category non-metric variable, low, medium, high, combined with a 2-category non-metric variable, gender of male versus female, will result in a 3x2 design with 6 cell groups. Sample size per group is a critical design issue as well. So minimum sample size per group must be greater than the number of dependent variables. And there is a recommended minimum cell size, which is 20 observations per cell or per group. And researchers should try to have approximately equal sample sizes per cell group. Covariates and blocking variables are effective ways of controlling for external influences on the dependent variables that are not directly represented in the independent variables. An effective covariate is one that is highly correlated with the dependent variables but not correlated with independent variables. Okay, MANOVA and ANOVA assumptions. So we had that earlier. So for the multivariate procedures used with MANOVA to be valid, okay, observations must be independent. Okay, variance or covariance matrices must be equal or comparable for all treatment groups. Okay, we also have the dependent variables must have a multivariate normal distribution, of course. Multivariate normality is assumed but many times hard to assess. Univariate normality does not guarantee multivariate normality, but if all variables meet the univariate normality requirement, then departures from multivariate normality are inconsequential. ANOVA F-tests are generally robust if violations of these assumptions are modest. Alright. Okay, let's go to the MANOVA estimation. Earlier, okay, we've discussed the 4 most widely used measures for assessing statistical significance between groups on the independent variables. So those are 1. Roy's greatest characteristic root, Wilks lambda, Pillai's criterion, and Hoteling's trace. And in most situations, The results or conclusions will be the same across all four measures, but in some unique instances, the results will differ between the measures. Maintaining adequate statistical power is also critical. Okay, so we have here some situations. Letter A, power in the 0.80 range for the selected alpha level is acceptable. Letter B, when the effect size is small, the researcher should use larger sample sizes per group to maintain acceptable levels of statistical power. The general linear model is widely used today in testing ANOVA or MANOVA models. It is available in most statistical packages such as our SPSS and SAS. Okay, how are we going to interpret and validate MANOVA results? So when covariates are involved in a global linear model, we're going to analyze the model with both the with and without covariates. And if the covariates do not improve the statistical power or have no effect on the significance of the treatment effects, then they can be dropped from the final analysis. Anytime two or more independent variables or treatments are included in the analysis, interactions must be examined before drawing conditions about main effects for any independent variable. And if the interactions are not statistically significant, then main effects can be interpreted directly because the difference between treatments is considered constant across combination of levels. And if the interaction is statistically significant and the differences are not constant across combinations of levels, then the interaction must be determined to be ordinal or disordinal. Okay, and when the independent variable has more than two groups, two types of procedures can be used to isolate the source of differences. Post hoc tests, examine potential statistical differences among all possible combinations of group means. So post hoc tests have limited power and thus are best suited to identify large effects. Planned comparisons are appropriate when a priori theoretical reason suggests that certain groups will differ from another group or other groups. Type 1 error is inflated as the number of planned comparison increases. Okay, so that ends our presentation. Thank you very much, classmates, for viewing and listening to our presentation.
We really hope that you really learned something from our discussion this morning.
That ends our presentation. God bless and stay safe, everyone.